In chapter 5, we talked about the um, behavior of ideal gas, and the main assumption we mentioned for any substance to behave as an ideal gas is that it should not have any intermolecular interactions. So if it doesn't have intermolecular interactions, all the molecules will be moving randomly and not interacting with each other in any capacity. Once you put the sample in lower temperature or high pressure, the molecules will start to slow down and become able to attract or interact with each other. And this is when any sample will be deviating from ideal gas behavior to real gas behavior. And as you lower temperature, you're giving a higher and higher chance for these intermolecular interactions to take place. And depending on how strong this interaction will be, the substance will be transforming into more and more dense phases. So it's with lower temperature, it's gonna go to a liquid phase, which is a more dense phase because of the higher intermolecular forces. And as you go to even lower temperature, is can eventually go to the solid phase with ultimately the highest type of intermolecular interactions. So what are the intermolecular forces or the intermolecular interactions? These are the interactions between the molecules themselves. And just in contrast to this is the interaction that holds the molecule together. This is called intramolecular interactions or bonding. And just to give a perspective on the magnitude of each of these, it would take you 41 kilojoules to vaporize 1 mole of water. And in order to vaporize 1 mole of water, you have to overcome the interaction between molecules. But if you want to break the bonds within the molecule in a molecule of water, you would actually need 930 kilojoules per mole of water. So the intermolecular forces are significantly weaker than bonding in any substance. And the direct measurement of the magnitude of intermolecular forces in any substance is associated with phase transitions. So anything that would require phase transition is going to have to overcome the intermolecular forces in the substance. So boiling something or melting something, so the boiling point or the melting point of any substance will depend on how strong or how weak these intermolecular forces are, and also the heat required to vaporize 1 mole of a substance, which is called the heat of vaporization, or the heat of fusion, the heat required to melt 1 mole of the substance, or the heat of sublimation, which is the heat required to sublime or transform 1 mole of the substance from the solid phase to the gas phase directly. All these processes are actually take place by overcoming intermolecular forces between molecules of the substance of interest. So what are the types of intermolecular forces that we know? There are several types. The first one is ion dipole forces. And these are the attractive forces between an ion in combination with a polar molecule. So the ion will have an electric charge, and the polar molecule will have dipole moment on it. This is why it's called ion dipole force. And this is actually the interaction responsible for dissolving salts in water, because when you put an ionic compound in a polar solvent like water, the dipole moment on the water molecule will orient itself to attract the negative end of the molecule with the positive ion, or the positive end of the molecule with the negative ion. And this type of attraction actually takes place, it's not just one molecule per ion, it's going to be several molecules per ion. And that's why it's strong enough to overcome the ionic bonding in these ionic compounds and dissolve it. And you can imagine, because this is an electrostatic interaction, it's the magnitude of the interaction is going to actually follow Coulomb's law, where you have the attraction force is going to be proportional to the magnitude of the charge on the two interacting objects, and inversely proportional to the distance or the size of the subjects. So you could consider ionic bonding as a type of intermolecular interaction as well. And in this case, the attraction inside ionic bonding is gonna be proportional to +1 charge on the cation times 1 minus charge on the anion divided by the distance between them, or the size of the ions. Just to put it in comparison, the interaction of an ion with dipole is going to be proportional to the charge of the ion times the charge of the dipole, which is going to be a fraction of magnitude of the charge. It's not going to be a whole charge. It's a fraction, like maybe we could consider it 0.5. So divided by the distance between them. So you could imagine that the interaction in case of ionic bonding is going to be significantly higher than interaction between ion-dipole interaction. So attraction in ionic bonding is going to be significantly larger than the attraction between an ion and dipole. But again, because this type of interaction here, each ion will be surrounded with several solvent molecules. This is why it is able to overcome the ionic bonding and dissolve the substance. This solvation power is going to be proportional to the charge on the ion. So the solvation power for a sodium salt is going to be, as expected, weaker than the solvation power of a magnesium salt because of the higher charge on the magnesium, right? The higher charge is gonna result in higher attraction between the salt and the water molecules. The second type of intermolecular forces is dipole-dipole force, and you should be able by now to predict what type of substances will exhibit this type of interaction. Dipole-dipole, it has to be a permanently polar substance, so it occurs in polar molecules, in polar substances between polar molecules. And in this case, polar molecules will orient themselves so that the positive end of one molecule is going to be oriented towards the negative end of the second one and electrostatically attracted towards it. And it's going to be propagating in all directions in the substance. And that's, again, a pure electrostatic attraction that follows Coulomb's law. So the magnitude of the attraction is going to be proportional to the charge, which is a partial positive charge, times the charge on the other dipole, which is a partial negative charge, right, divided by the distance. So you could imagine that this is going to be weaker than the attraction in case of ion dipole, which is weaker than the attraction in ionic bonding, right, or ionic compounds. So let's discuss this question here to decide which type of substance should exhibit dipole-dipole interaction. As we said, it has to have permanent dipole moment on it. So it has to have be polar substance. So you should check each of these options And based on your previous knowledge from chapter 7, you should be able to decide which one of these substances is polar and which one is not. So if you consider the first one, this is iodine, right? It's linear molecule with a completely covalent nonpolar bond. So that's a nonpolar substance. So you're not expecting dipole-dipole interaction in a nonpolar substance. Carbon dioxide, if you draw the low structure, it should be a linear molecule that looks like this. It has polar bonds between the carbon and the oxygen, and another polar bond with a dipole moment running from the carbon to the other oxygen. But because they are exactly opposite with respect to each other, they cancel each other, and the molecule is overall non-polar. So again, that's not expected to show dipole-dipole interaction. Same thing for BF3. It contains polar bonds. However, these polar bonds are symmetrically oriented around the central boron atom, so they completely cancel each other, right? So and the whole molecule is gonna become nonpolar, which means it should not exhibit dipole interaction. The only molecule that has polar bond and the dipole moment of the molecule does not cancel at all is HBr, and the dipole moment will run from the positive hydrogen to the negative bromide. And again, it's a permanently polar molecule, so that is the substance that is expected to show dipole-dipole interaction. A special type of dipole-dipole force is called the hydrogen bonding. And a hydrogen bond will form if the substance or the molecule contains a nitrogen-hydrogen bond or oxygen-hydrogen bond or fluorine-hydrogen bond in combination with another part of the molecule that contains nitrogen, oxygen, nitrogen, or fluorine. So what you need to have is at least a nitrogen hydrogen or oxygen hydrogen or fluorine hydrogen bond in your molecule, and then one other part of the molecule should contain either nitrogen, oxygen, or fluorine. Any combination of any of these will develop hydrogen bonding. Hydrogen bonding is going to be a dipole-dipole attraction between the dipole moment on the nitrogen, oxygen, hydrogen, or fluorine hydrogen, and either nitrogen, oxygen, or fluorine. So something like water, for example, here, as you can see, we have a oxygen hydrogen here, and a second molecule will have oxygen. So the dipole moment of this oxygen hydrogen bond will be electrostatically attracted to the oxygen on the second molecule, and this is called a hydrogen bond here, right? Same thing in ammonia. We have NH in combination with N. The interaction between both of them is hydrogen bonding. Even a mixture of both substance will have NH in combination with oxygen. So again, that's another site of hydrogen bonding interaction. Or you could consider the other way around, oxygen hydrogen bond interacting with nitrogen on ammonia. This is one other site of interaction for hydrogen bonding. Combination of ammonia and HF, NH is going to interact with F, right? Or you could consider the other arrangement, the FH bond interacting with nitrogen moiety on the ammonia side. So why hydrogen bonding is special, why we consider it a special type of dipole-dipole interaction. If you look at the trend of boiling point for any substance, and if you look at this series right here, you will find that the boiling point decreases as the molar mass decrease. So as you go to smaller molar mass, you will have lower boiling point. That trend holds for these three series right here in the first part. Yes, when you go to from the higher molar mass to the lower molar mass, you find that the boiling point decreases. And if this trend holds, you should have expected water to boil around negative 100 degrees Celsius, and HF should be something on the same scale, and NH3 is going to be the same as well. In reality, these three substances boil at much higher boiling points, and the only reason for this significantly higher boiling point for water, HF, and ammonia is because these three substances contain hydrogen bonding. So these three substances or the hydrogen bonding in these three substances are significantly strong, that it actually causes something like water to go from a predicted or expected boiling point of negative 100 degrees Celsius to 100 degrees Celsius. This is a significant effect, and we actually owe the whole life for this phenomena right here. And it's also responsible for something as important in biological systems, which is the stability of DNA molecules. DNA molecule is a double strand of nucleic bases, which are actually held together with several sites of hydrogen bonding. So without these strong interactions between the nuclear bases in DNA, it would have not been stable at all, and it should have not been a double helix as it is. So it's actually responsible for the stability of something very important to all the living organisms. So let's exercise how to again decide or predict whether a substance or a combination of substances should exhibit hydrogen bonding or not. So if you mix water with any of these substances here, which one are you expecting to see hydrogen bonding in? Again, we have water. Water contains OH, and what we need for a hydrogen bonding interaction to happen is combining this OH bond with either nitrogen, oxygen, or fluorine. So any substance that contains nitrogen, oxygen, or fluorine should be able to exhibit hydrogen bonding in combination with water. So if we apply these to that first substance here, so as we said, we have OH in water, and we have O in this substance right here. So this is a possible site for hydrogen bonding interaction between these two substances. So that combination should exhibit hydrogen bonding. If you look at methane, if you combine methane with water, there is none of the required combinations that would exhibit hydrogen bonding here. So in this case, you should not expect hydrogen bonding in this combination. If you combine water with F2, right, that's one of the combinations here. So OH with F, that's a possible site for hydrogen bonding, right? This one here, if you combine water with this formic acid, you will find that you have OH on water with H on the formic acid. So that's a possible site for hydrogen bonding. We could actually do it the other way around. You have OH on formic acid that could interact with the oxygen on water molecule as another site for hydrogen bonding. So several possibilities for hydrogen bonding in this case. If you combine sodium with water, again, no combinations of the three possible combinations that should exhibit hydrogen bonding. So this is not gonna have hydrogen bonding in it, okay? So the last type of intermolecular force, and it is the weakest type of intermolecular force, is dispersion force. And this type of force is, again, another type of electrostatic attraction between the molecules that will develop because of induced dipoles. So even if it is a completely nonpolar substance, if you put completely nonpolar objects like two helium atoms nearby each other, the nucleus of atom 2 will be able to slightly attract the electron cloud of atom 1. So that is gonna shift the electron cloud on atom 1 slightly to the left. So it's gonna be slightly positive, negative, partial negative charge on this end, and that's gonna leave the second or the other side of the atom electron poor, so it will have a slightly partial positive charge. So that's an induced dipole that is gonna only develop because you put a second helium atom nearby the first atom. So if this atom here is not nearby at all, this dipole moment should have not been developed. But the fact that you actually developed an induced dipole moment on this nonpolar object would develop some type or some degree of electrostatic attraction between the positive end of one of them and the negative end of the other. This type of attraction or this type of interaction is called dispersion forces. And it is possible to induce similar temporary dipole moments on nonpolar objects if you put anything that would induce a distortion in the electron cloud of the molecule. So if you put a cation beside a nonpolar molecule, what happens is that the cation will attract the electron cloud slightly towards itself. This is gonna form a partial negative charge on this end, and it's gonna leave this end electron poor, and it's gonna make it partial positive. So this is an induced dipole that developed only because you have this cation nearby. And once you have this induced dipole, there is a possibility for electrostatic attraction between the two objects. This type of electrostatic attraction is one of the types of dispersion forces that is called ion-induced dipole interaction. So it's ion interacting with an induced dipole. And you can make an induced dipole in any nonpolar molecule with the permanent dipole. So if you mix a nonpolar molecule with the polar molecule, the permanent dipole of the polar molecule will do the same thing. It will attract the electron cloud of the nonpolar molecule slightly towards itself. It's gonna make this end partial negative and leave this end with partial positive. So it induces an electric dipole moment on the nonpolar molecule, and that will make it possible for electrostatic attraction between the two molecules. And in this case, this type of interaction is called dipole-induced dipole interaction. So the magnitude of dispersion forces is proportional to an atomic property called polarizability. polarizability is basically how easy it is to shift the electron cloud distribution in an atom or a molecule. So if the molecule is all alone, or the atom is all alone, is going to have the electron cloud symmetrically distributed, like spherically distributed around the nucleus. Depending on the polarizability of this atom, it might be easy to shift this electron cloud one way or the other. And in this case, if you shift it, you will be able to make the atom have a partial negative charge on one end and a partial positive charge on the other end. How easy it is to shift the electron cloud depends on the polarizability, and the ease of shifting electron cloud of atoms or molecules will basically depend on how far the electron is from the nucleus. So the further the electron is from the nucleus, the easier it will be to shift it away from the nucleus. So it's gonna be higher polarizability with more diffuse electron cloud, which means larger size, and a greater number of electrons, which is again is gonna mean that it's larger electron cloud. Uh, so so that means that dispersion force is gonna go higher as polarizability goes higher. So, and polarizability goes higher with higher size, which is larger for higher atomic numbers. So any atom with larger atomic number will have higher polarizability, which will cause the dispersion forces to be higher, right? So, and this is actually manifests itself very clearly when you compare the melting point of methane with all of this series right here. So melting point of methane is -182. So it's actually a gas at room temperature. And as you go from hydrogen to fluorine, chlorine, iodine, bromine, and iodine, you're actually having higher polarizability in the terminal atoms, which make it easier to shift the electron cloud, or easier to develop stronger dispersion force. So the higher the polarizability means stronger dispersion force, and the stronger dispersion force means that you would need much more energy to overcome the interaction or the attraction between the molecules in order to melt it or boil it. So the stronger dispersion force will result in higher and higher melting point. So let's exercise here how to predict different type of intermolecular forces in a substance. Again, that is going to depend on our knowledge about the nature of the substance, whether it's nonpolar, polar, or ionic. So if you combine these two substances here with each other, what do you expect? The first step, you have to decide what type of substance each of them is. So HBr is polar, H2S is also polar. So this is gonna be a polar-polar, which means dipole-dipole interaction. Right? This second combination here, chlorine is non-polar. CBr4 is also non-polar, so there is no special type of interaction. The only possibility is that they have dispersion forces, as we explained in the previous slide. Here, iodine is non-polar. Nitrate is an ion. So this is again, one type of the dispersion forces, which is the ion induced dipole interaction, which is going to happen because you have a negative ion close to the nonpolar iodine molecule, which is again going to shift the electron cloud slightly away from the ion. So that is going to cause a partial positive charge on this end and makes the other end partially negative, and this is gonna make it possible for electrostatic attraction between the ion and the induced dipole on the iodine molecule. Here, ammonia is polar, and this molecule here, even if you don't know it, it's only containing carbon-hydrogen bonds, which means it only contains non-polar bonds, covalent bonds, so it's going to be non-polar, right? Um, so even without knowing the identity of the molecule, you have a combination of a dipole with non-polar molecule that is going to get induced dipole by the fact that you have a permanent dipole nearby. And again, this is a special type of dispersion force, one of the three types of dispersion forces. So this molecule here is actually benzene. It looks like this. And what happens is that when you put the dipole moment of ammonia molecule, which has a permanent dipole on it, is gonna again rebuild the electron cloud on the other way, so it's gonna have a partial negative charge on this end and a partial positive charge in this end. So this is an induced dipole that will develop on the nonpolar benzene molecule, and you have a permanent dipole on the ammonia molecule. So that's a potential site of electrostatic attraction between both of them, which is the dipole-induced dipole interaction or the dispersion force. Just to summarize what we discussed so far about the different types of intermolecular forces in substances and how they compare with each other in magnitude, all of these are actually electrostatic attractions. So they follow Coulomb's law, which says that the magnitude of the attraction is going to be proportional to the charge of the first object and the charge of the second object divided by the distance between them, or the size of the two objects. So if you start with completely no interaction, this is the case in ideal gases. So no interaction at all. And once you start developing more interactions in the substance, the first type of interactions that could develop in any substance, and it doesn't need any special nature for the substance, is dispersion force. As we said, it's possible to find it in polar, non-polar, or ionic compounds. All of these will exhibit dispersion forces. And because it's an interaction between induced dipole, which is very weak, partial charge, and induced dipole, another induced dipole, which is another very weak partial charge. So that means it's going to be the weakest type of intermolecular interaction because it has the smallest electric charge on the molecule. Slightly stronger than this is dipole-dipole interaction, because the magnitude of the electric charge on the dipoles is going to be higher, which is going to make the attraction higher. So dipole-dipole interaction is stronger than dispersion forces. And as we said, hydrogen bonding is a especially strong type of dipole-dipole interaction. and on the same magnitude is the ion-dipole interaction that occurs in solution, because you have an interaction between a full charge on the ion and a partial charge on the solvent molecule. So that's, of course, is going to be significantly larger than the dipole-dipole interaction, which is between partial charges. Of course, all these types of intermolecular forces are going to be significantly weaker than bonding within any molecule, like any ionic interaction or covalent interaction. Those are going to be significantly stronger because, for example, ionic interaction is going to be an attraction between a full charge on the cation times a full charge in the anion. So again, significantly higher charge will make it significantly higher attraction or significantly stronger type of interaction. So what is the significance of these different types of intermolecular forces and the significance of how strong or weak they are? They actually affect the phase of the substance, whether it should exist in gas phase, liquid phase, or solid phase. And the first macroscopic property that it's going to affect is the vapor pressure. Vapor pressure is the gas phase pressure of a substance in dynamic equilibrium with the pure liquid. So if you put a liquid of a certain substance in a closed container, what will happen is the solvent molecule, the substance molecules on the surface will feel much less attraction to the liquid molecules and will have much stronger kinetic energy. So they will have enough kinetic energy to escape and become vapor. And on the other hand, if you have a lot of these vapor molecules, they will collide with each other, and some of them will slow down enough to condense back to the liquid phase. And this process will continue till it becomes in equilibrium, which means the number of molecules that escape the liquid phase to the gas phase will equal the number of molecules that escape the gas phase to the liquid phase. And the amount of gas molecules or vapor molecules will be constant. That amount of vapor molecules is called the vapor pressure of the substance. And you can imagine that this vapor pressure is going to depend on the strengths of intermolecular force that this substance exhibit. So if you have a polar substance, you should expect a stronger type of intermolecular forces, which is the dipole-dipole interaction, right? And because the molecules exhibit stronger intermolecular forces, is going to make it very difficult to escape the liquid phase to the gaseous phase. So the evaporation rate will be slow, which means the vapor pressure will be smaller. And in this case, we call the substance non-volatile substance. In contrast, if you have a non-polar solvent, what happens is that it actually exhibits a very weak type of intermolecular force, which is the dispersion force, right, as we discussed earlier. And because the intermolecular force is very weak, it is very easy for the liquid molecules to escape and evaporate to the gas phase and overcome the weak intermolecular force. So it's going to make the evaporation much faster, right? Which will make the vapor pressure much higher. And this type of substance, is going to be called volatile substance. because it's very easy for these to evaporate much faster than the non-volatile substances. One other factor that affects vapor pressure is actually temperature, because as we previously discussed in chapter 5, kinetic energy of molecules is proportional to temperature. So the higher the temperature, the higher the kinetic energy, which means the easier it is or the faster it will be for the molecules to evaporate, right? Um, so once you start increasing temperature, this is gonna start increasing the vapor pressure of the substance till it actually equals the external pressure. And in this case, all the substance will exist in the gas phase, or it will boil. So for atmospheric pressure, that temperature that will cause the vapor pressure of water to equal 1 atmosphere is going to be 100 degrees Celsius. And this is called the normal boiling point, right? But you should be able to see that it is possible to make the substance boil at much lower temperatures if you make the external pressure lower. So if you put the substance in external pressure that is 380, for example, you should expect water to boil at 80 degrees instead of 100 degrees, and vice versa. If you put it at something like higher than 1 atmosphere, it's gonna boil at higher temperatures than 100 degrees. So the it's not one boiling point, it's several boiling points depending on the external pressure, but the one that corresponds to 1 atmosphere, which is the standard pressure, is called the normal boiling point for the substance, and it is 100 degrees for